Welcome to the lecture of Interfacing 7-segment display with 8051 microcontroller. This is the 3D image of 7-segment display. We can display here digits and it is having a 10 terminals. The terminals are named as A, B, C, D, E, F, G. One terminal is referred as dot and the two common terminals are there. So it is 10 pin IC. These are the pin numbers 1 to 10. So we can display any digit 0 to 9. Now there are two types of 7-segment display. The first type is common cathode display. In common cathode display, the all cathode terminals of these segments, each segment can be treated as one LED. So all cathodes of these LEDs are connected to common terminal, that is ground, and the anodes of LED are available to apply input. So to glow a particular segment or to turn particular segment on in common cathode display, we have to connect here logic 1. So user has to apply a logic 1 at this input of segment terminal to glow a particular segment. The second type is common anode display. In common anode display, all anode terminals of this display are connected to VCC. So all anode terminals are common and that's why it is called common anode display. And user can apply input to cathode terminals of the segments A, B, C, D, E, F, G. The H terminal, that is DP terminal, that dot terminal, also we can turn off. If you are interfacing multiple displays and you want to use the dot also, then you can use this. The terminal G is referred as a input terminal for this DP, that is dot. That is not shown here, but that can also be used. So in common anode display, whenever user will apply a logic 0 as an input to this cathode terminal, the particular segment will glow. So these are two types of display. We can use any display for our application. Now to display digit 0 to 9, here the patterns are shown which segment should be turned on. So for example, to display 0 here, this segment A, B, C, D, E and F should turn on and segment G should turn off. Here DP is not used, so that is also off. So this 6 segments should be turned on to display logic 0. Now whether you are going to apply logic 0 or logic 1 to turn these segments on depends upon which type of 7-segment display we are using. If it is common cathode display, then we have to apply logic 1 to segment A, B, C, D, E, F. So this particular segment will turn on. If we are using common anode display, then we have to apply here logic 0 so that this segment will turn on. To display 1, segment B and C should turn on. To display 2, this segment should turn on. So like that, we can turn the particular segment on to display a particular digit. Now to display a particular digit, as we have seen, the particular segment should turn on. So for that, we have to find the 7-segment code. So in this table, the example of finding a 7-segment code, this is the 7-segment code for common cathode display is shown. So these are the digits. Suppose we want to display a digit 0. We have seen that this A, B, C, D, E, F, this segment should be at logic 1. So this segment should turn on. So since it is common cathode display, we have to connect these segments to logic 1 and this G and H dot we are not using should be connected to logic 0. So to the 7 segment display, we have to apply this pattern of data 00011 and 1111. So if we convert this binary data into hex, we'll get this value as 3F. So 3FH, if you give as an input to display, common cathode display, then it will display a digit 0. Similarly, when we want to display a digit 1 on common cathode display, we have to apply input logic 1 at C and B segment. All other segments will be at logic 0. So again convert this into hex, we'll get data 06H. So similarly for all these display, we can find this 7 segment data. So this is the 7 segment code which we have to give as an input to segment through microcontroller or through any IC to display a particular digit. This is for common cathode. In the same way, you can find the 7 segment code for common anode display also. For that, in that case, for common anode display, instead of logic 1, here we have to apply logic 0. So for all these bits, we have to apply logic 0. For all A, B, C, D, E, F, logic 0 should be applied. For H and G, we have to apply logic 1. And then we can convert this data into hex. Or we can directly complement this data 7 segment code of common cathode display to get a 7 segment code of common anode. So this is how we can find the 7 segment code to display a digit 0 to 9 on display. Now instead of directly giving 7 segment code to common cathode or common anode display, we can use the ICs which are available, which are used to convert a BCD input into 7 segment code. So no need to manually find this 7 segment code for the digits 0 to 9 digits. We can use IC. As an example, here this IC is shown 7447 IC, which is BCD to 7 segment decoder IC. This IC will convert input BCD number into 7 segment code. So 7 segment code will be available as an output at this IC terminals. So here we can provide 0, means all these 4 terminals, input terminals will be at logic 0 for 0 digit, and it will give you the 7 segment code for digit 0. If you want to display 1, digit 1, then write here 00001 BCD 1 input. It will convert into 7 segment code, and that will be given to this IC. Here the common anode IC is shown. Similar way, you can apply a digit 0 to 9 digit as a input. IC will convert it into its particular 7 segment code, and that digit will be displayed on this display. Now here this current limiting resistor we have to use. Now how to find the value of this current limiting resistor? It depends upon which LEDs are used in the display. So the current depends upon the color of LED. As an example, here we'll see if the current through this LED is of 20 milliampere. So that is written in ampere, 0.02 ampere. That is the current flowing through this LED. And the voltage drop across LED when it is on is 2.2 volt. It depends upon which LED you are using. So from the data sheet you will get this value. And this is the input voltage. In our case it is 5 volt. So using this circuit we can find the value of current limiting resistor. That is R is equal to input voltage 5 volt minus the forward voltage. In this case it is 2.2 volt and divided by current, that is 0.02 ampere, 20 milliampere. So value of resistor is 140 ohm. So you can use resistor greater than 140 ohm value. Now this is the interfacing diagram of 7 segment display, common cathode 7 segment display with 8051. Here 8051 IC 8089S51 is used. You can use any other 8051 IC to interface 7 segment display. Here reset circuit is shown, which is used to reset the microcontroller, and crystal connections are also shown. EA terminal, external address terminal, is connected to VCC, that is 5 volt, and 5 volt is connected to VCC. Pin number 20 is ground. And these segments, A to H segment, H is used for dot, these are connected to port 1 of microcontroller. So P1.0, that is lower bit of this port, is connected to segment A, and the upper bit is connected to segment H. So the 7 segment code which we have seen how to compute it, that we can use directly to display a digit on this common cathode display. To display a particular digit on this common cathode display, we have to just send a 7 segment code of that digit on port P1. So if you send a 7 segment code of digit 0, that is 3FH we have computed, on this port P1, it will display 0 digit on this display. If you send a code of 1, digit 1, it will display digit 1 like that. But now we'll write a program to display digits 0 to 9 continuously on 7 segment display. So what we'll do, we'll send a 7 segment code of digit 0 to microcontroller, then we call a delay, then we'll send a 7 segment code of logic 1, we call a delay. We'll repeat this step for all 9 digits, and again we'll repeat whole this program continuously. Now we'll write this program from the starting address 000H. You can change this address also. For that, this org assembler directive is used, which will store this program at this address 000H. Now here in this program, we'll use a lookup table method. The lookup table name is given as string. You can use any other name, and the all values in lookup table we are storing as a 8-bit value. So for that we have to use here assembler directive db. db indicates 8-bit value, and here I have stored this 7 segment code for digits 0 to 9. So 3FH is a 7 segment code for digit 0, 06 for digit 1, 5B for digit 2, and the 6F for digit 9. So all these values, 7 segment code values, are stored in lookup table. So at first memory location of this string whose name is given as string, at first memory location 3FH is stored. At next memory location 06H is stored. Next memory location 5BH is stored. So like that this lookup table will store the value in memory location. Assume that these are the memory location, and to this first memory location here somewhere name is given as string. So this string will point to first value, that is for digit 0, and which is 3FH. At next memory location, the value for digit 1 will be stored, that is 06H. So like that this lookup table values will be stored in memory, and name given to this lookup table is string. So whenever we'll point to this string memory, name of lookup table, it will point to this first value. And after that we have to increment this to point to next memory location. So first we are storing 10 values in lookup table. So we'll read these values one by one and we'll send it on port P1 because segments are connected to port P1. So 10 values we want to read. So I have initialized here counter. So R0 register is used as a counter and it is initialized with value 10, 0AH in hex. The next is we'll use a DPTR register, that is data pointer register, to point this lookup table. This instruction we are going to write in program memory only. So this is the part of program memory. So we are reading a ROM memory. So to read a data from ROM memory, we are using here DPTR register. So when you use this type of instruction, DPTR comma hash string, then the address of this location, suppose for example string is stored, this lookup table is stored at address 2000h, this is just an example, then 2000h will be stored in DPTR. So we are using DPTR register to point to this memory location. So the starting address of string lookup table is stored in DPTR. The next is we are initializing accumulator A with value 00H and then we'll read a data from this lookup table. So for that we'll use movec instruction because we are reading a data from program memory, and to read a data from program memory the instruction is movec. So we'll use this instruction A comma at A plus DPTR. The A is initialized to 0 and starting address of lookup table is stored in DPTR. So what this instruction will do, it will go to this address location, and in this example address is 2000 because 2000 is stored in DPTR, and which is the first memory location of this lookup table. So the controller will read a data from this address location, that is 3FH, and store it back into accumulator. So the 3FH is now stored in accumulator. We want to send this 3FH, that is code of 0, on port P1. As soon as we place this code on port P1, the digit 0 will be displayed on our display. So we'll give some time to display second digit. So we'll call a delay program. You can write any simple delay program or delay program using timer. That is explained in timer delay video. Now after that we'll increment this DPTR because we want to display a second digit and the code of second digit is stored at next memory location. So we'll increment this DPTR. So DPTR will point to second memory location. As an example, in this case 2001 will be stored in DPTR. So we have incremented DPTR. Now we have displayed one digit. So we'll decrement a counter and we'll check whether it is 0 or not. That means all 10 digits are displayed or not. So for that we have used here instruction DJNZ. Decrement this counter R0 by 1, and if it is not 0 then go to label back. So what it will do, now in accumulator the value of 7 segment code is stored, will store 0, will initialize accumulator again with 00, and DPTR is pointing to next memory location. That is where the code 06 is stored, that is code of digit 1 is stored. We'll add this content 00 with DPTR and we'll read that digit 7 segment code which will be stored in accumulator. We'll place the contents of accumulator on port P1. So now digit 1 will be displayed. We'll call a delay and we'll increment accumulator again, so that it will point to the next digit 7 segment code. Again decrement a counter. So this steps we want to repeat 10 times. So which will display a digit 0 to 9 with some delay. After displaying all this, all 10 display, our program is continuously display 0 to 9. After displaying 9, again go for 0. So what we'll do, without checking any condition, we'll jump to start. So again we'll start a program. We'll initialize a counter. Again DPTR will point to first memory location. We'll read a data stored at this memory location and we'll place it on P1. So this program will continuously display digit 0 to 9 on 7 segment display. So this is just example of interfacing one 7 segment display. We can interface multiple 7 segment display also. Now sometime in exam also the question may be asked, interface two displays. You can interface more than one display. So in this example, two displays are interfaced and display number. Some numbers may be given to you. Suppose number 0, digit 0 I want to display on first display and digit 1 should be displayed on second display. So to interface these two displays, what logic we can use is we will enable one display at a time. These data lines, that means segment lines of this both displays are connected in parallel. That means same port is used to connect the segments of first display and segments of second display. So this line P1.0 is connected to a segment of first segment as well as a segment of second segment. So all these lines are connected in parallel. That means whatever code you will send on this port, that will be given to display 1 as well as display 2. So suppose when you are sending 7 segment code for digit 0, that will be given to first display as well as second display. So if both displays are enabled, on both this display 0 will be displayed. But we don't want to do that. We want to display 0 on first display and 1 on second display. So what logic generally uses, at a time enable only one display. That means first enable this D1, send code of 0. So 0 will be displayed here. Since this display is disabled, no digit will be displayed here. After that, immediately we'll disable this display 1 and we'll enable display 2 and we'll send the code of 1. So 1 will be displayed on second display because first display is disabled. So enable one display at a time, send a code which we want to display on that particular display. After that, enable next display, send a code. Like that, you can use to interface a multiplex display. Enable one display at a time. You can use any logic to enable the display. Here logic uses at this common terminal of display, transistors are connected. To make it simple, you can show inverter also. So P3.0 is connected to base of this transistor, which is connected to common terminal of display 1. P3.1 is connected to base of this Q2 transistor, which is connected to common terminal of display 1. When we send a logic 1 at P3.0, this Q1 transistor turns on and common terminal will be connected to ground. So to enable display 1, we'll send a logic 1 on P3.0. At that time, we'll send a logic 0 on P3.1. So since 0 is connected to Q2 transistor, it will be turned off and this common terminal will be in hanging state. So 1 will be connected here, that is high impedance state. It won't be connected to ground. So this display will be disabled. So to disable first display and enable second display, we have to send logic 1 on P3.0 and logic 0 on P3.1. Similarly, next time we'll send a logic 0 on P3.0 and logic 1 on P3.1. On port P1, we are sending a code. P3.0 is at logic 1 to enable display 1. P3.1 is at logic 1 to enable display 2. So we'll write a simple program to display digit 0 and 1
on these two displays, and that we can do continuously 0 and 1 will be displayed on this digit. So we'll write a org assembler directive. So 0 1 we are going to display. So what first instruction I have used here, set B P3.0. That means first display is enabled. Logic 1 we are sending to common terminal of display 1, and at the same time we are sending 0 on P3.1. So we are clearing P3.1. So display 1 is enabled and display 2 is disabled. Display 2 is disabled because we have sent logic 0 on P3.1. So since we want to display digit 0 on first display, now we'll send a 7 segment code of 0 on port P1. So 3FH is the 7 segment code of 0 that is directly given to port P1. So simple program we are writing here, because at a time only one display is enabled and digit is displayed on one display only. But this process is so fast that due to persistence of vision, we'll observe that both digits are displayed continuously on the display. So next time what I am doing, I am sending logic 1 to transistor of second display. So set bit 3 P3.1, exactly opposite to this 2, and then clear P3.0. So first याचा transistor आपण 0 पाठवते. So second display is enabled now. First display is disabled. On second display, we want to display digit 1. So we'll send a ASCII value of 106H on P1. ASCII value depends upon which type of display you are using. So P1, on P1 we are sending ASCII value of 0, 7 segment value of 1. So after that, I'm using here instruction sjump start. That means repeat this continuously. Enable first display, send 7 segment code of digit 0, then disable first display, enable second display, and send the 7 segment code of digit 1. And do it continuously, repeat it continuously.